students, and welcome to Panel Educate. In this video, we'll be looking at um, combination of events. We'll try and look at mutually exclusive events, additional, and we'll look at complementary events. Okay, now two or more events which are subsets of a sample space. Two or more events. Let's say event E1 is a subset of S. So that means E1 has component of S. Okay, and maybe event E2 is also a subset of S. Now, these three events, event E1 and event E2, can be combined using the set notation, union of set or intersect of set. It's a union of set, okay, or intersect, okay, of set. Now, event E1, E1 union of E2 is the event that either E1 or E2 or both occur. Okay, this is the event of either E1 or E2 or both occur. Okay, then why we have event E1 intersect E2 is the event that both E1 and E2 occur. Alright, so that's the events that both E1 and E2 occur. That's for the intersect. Now, if you look at just take this one out. Normal set theory, when we're talking about union of a set, okay, when you have union of a set, say this is E1 and this is E2, okay, this is the intersect of a set. So let's now say that E1 has, contain this component, maybe 1, 2, 3, 4, 6, 7. Okay, we have E2. It also contains, let's say 2, 4, 6, 8, 9, 10. Now let us look at event E1, okay, union E2. In our set theory, what do? You look at the ones that have, the numbers that are the same with this, and the ones that are not the same. For example, E1 union E2 will be this one is here, it's not there, so we'll pick 1. Okay, 2 and 2 is here, okay, we'll still pick 2, because union means all the elements of E1 and E2 are in the association. Okay, you can watch my video on set theory. If you are still having issues on this, you can watch the video on set theory. Now we have the union. That's the union of maybe the husband and wife. They may have something common, okay, and they may have something that they don't have in common. All right, so this might be television, house, iron, and all that. So if they are getting married together, that's the union of the two of them. So and they have the same iron, they might just want to say, let's just pick one iron, okay, or no, okay, you have a television, okay, and I don't have a television, then I'll pick a television. Okay, 2, we both have iron, I'll just pick iron. Okay, 3, we don't have, I have, you don't have, so let's pick the one I have, like that. 4, okay, then 5 is not there, but we do have 6, okay, we just pick 1, 6. I have 7, you don't have 7, okay, I just pick 7. Then 8, 9, 10 is what I don't have, 8, 9, and 10. So if you look at it, you have all the components of E1, 1, 2, 3, 4, 5, 1, 2, 3, 4, 6, 7, 1, 2, 3, 4, 6, 7. It's going to be there. Okay, then all the components of E2 is going to be in the union, 2, 4, 6, 8, 9, 10. 2, 4, 6, 8, 9, 10. So that is the union of the two events. Then when you now have the intersect, that is E1 intersect E2, it's just what they have in common. And what they have in common are these 2, 2, they have 4 and 4 in common. They have 6 and 6 in common. 8 is not in common. Okay. 9 is not in common and 10 is not common. So this particular one will be 2, 4, and 6. All right, so that's why we say that event of E1 union of E2 is the event that either E1 or E2, either E1 or E2, look at it now, either E1 or E2, E1 and E2 they are contained, or both occur. Okay, that's why we said that. And why we said the event E1, okay, intersects E2 is the event that both E1 and E2 occur. That means what is common to the two of the events. Now let us look at mutually exclusive events. Look at mutually exclusive events. Now for a mutually exclusive event, two events E1 and E2 are said to be mutually exclusive if they cannot both occur simultaneously. Okay, we said E1 and E2 are mutually exclusive if E1 and E2 cannot both occur simultaneously. Okay, so that is what we mean by mutually exclusive events. And in set theory, that is in set theory notation, we can say that two sets E1 and E2 are disjoint. Okay, what we'll say in set theory is that they are disjoint. That means if they cannot both occur simultaneously, that's what we say that E1 and the intersect E2 is a null set. That means it doesn't occur. So, and the probability of such E1 intersect E2 is also 0. So what it means is that E1 and E2 cannot are mutually exclusive because they cannot occur simultaneously. So you have a set like this. You have an E1, then you have an E2. E1 is here, E2 is here. So there is nothing that is here. So the intersect here, E1 intersect E2 is actually none. It's nothing. It's there. There is nothing there. 0. Okay. Now let us look at addition law. All right. So now from the set theory, looking at addition law, from the set theory we have that okay, the number of events, that is if E1 union of E2 then is equal to E1 plus E2 minus E1 and intersect E2 rather. Okay, so now the union of sets is you had this plus this, then you minus this place from it. Okay, that's what makes the union of sets. So now, since the sample space is not equal to 0, okay, so then we can divide all these components with the sample space. So we have E1 union E2 divided by sample space go to this one, E1 divided by sample space plus this E2 sample space minus n E1 intersect E2 divided by the sample space. Now, this is a probability because probability is when you have probability of an event, okay, is the number of components in that particular event over the total number of sample space. All right, so this particular one is the probability of E1 union of E2. Okay, then this is probability of E1. As probability of E1 is number of elements in the event E1, then over the total number of components in the sample space. So we have probability of E2, then minus probability of E1 intersects E2. Okay, now if we have E1 and E2 as mutually exclusive, so if it's mutually exclusive, that means we have something like this. Okay, if we have E1 as mutually exclusive, then we are going to have this. Okay, this is going to be E1, going to be E2. So what it means is that this intersect here is 0. So that means this one will give us 0. So then we have the probability of E1 union of E2. Okay, will be probability of E1 plus probability of E2. That is for a mutually exclusive event, which shows that E1 and E2 are disjoint. This particular one shows E1 and E2 are disjoint. All right, so let us quickly look at some examples. Now, in a single throw of a fair die, what is the probability that an odd number or a perfect square greater than 1 show up? Now, we know that in a die, you can only have 6 things happening. So that you're having a 1 showing up, a 2 showing up, 3 showing up, 4 showing up, 5 showing up, and 6 showing up. Okay, you have a die like this. Okay, you have something like that. Okay, let me draw that again. I think can do better than that. Okay, so let's say you have a die. Okay, it's just like a die. You may have 1 here, you have 2 here, you have 3 here. Okay, you have 4 here. Okay, and you can also have they have 8 sides. 1, 2, somewhere here can be 5. Okay, like that. So this is just the side of a coin. It has 6 sides. 1, 2, 3, 4, then 5, 6. That's 6 sides. So we can only have 1, 2, 3, 4, 5, 6 appearing. Now let us say E1. So let E1 be event that odd number show up. So if that is an event of that odd number show up, we're going to have odd number to be 1, 3, and 5. That is odd number. Okay, so let us say E2 is an event that even number that let's say E1 be the event that a perfect square that is greater than 1 show up. So what is the perfect square now? Now, the only event that will give us a perfect square greater than 1 will show up is only going to be 4. Okay, because we are told that what is probability that an odd number or a perfect square greater than 1 occurs. So we have two events of odd number or a perfect square greater than 1. So the second event that a perfect square greater than 1 occur is just only 4 that is there for event E2. Now, as you can see here, looking at the components of or the element of E1, event E1 and event E2, E1 intersect E2 is not is 0. Okay, because there is no intersect between E1 and E2. So, which means event E1 and event E2 are mutually exclusive. Okay, that's what you need to know. Event E1 and event E2, they are mutually exclusive. So you can treat it with the formula that we have. That means the event of probability of E1, okay, union of E2, okay, is probability of E1 plus probability of E2 because they are mutually exclusive. So probability of E1, which is this, we have 3, 1, 2, 3, and our sample space is 6, which is all in went there 1, 2, 3, 4, 5, 6, and the sample space for E1 is 3. Sample space for E2 is 1. Okay, so let's look at that now. This particular one there be this is 3, which is probability of E1 3 over 6, which is sample space 3 over 6. Then probability of E2, which is 1 over 6. So if we do that, we're going to have 4 over 6, so which is 2 over 3. Okay, so that is the example that we can take them. Now, additional law can also be extended to 3 or more events. It can also be extended to 3 or more events. Now, in the case of 3 events, it can be written as probability of E1, union of E2, union of E3. That's 3 events. Then we're going to have probability of E1, just like the way we did before. You add all the probability of all the events, E2, plus probability of E3. Then don't forget to do your minus probability of the intersects. All the intersects. E1 will intersect E2. Okay. Then minus probability of E2 we also have, intersect of E3. Okay, we're going to have minus probability of E1 intersect E3. Then you're going to add plus probability of E1 intersect E2, then intersect E3. So it can also be added like this. However, if E1 and E2 and if E1, E2 and E3 are mutually exclusive, then all of this one also will be 0. This one will be 0, this one will be 0, this one will be 0. So what we have will be probability of E1 plus probability of E2, just like when we do for 2 events, for probability of E3. So don't forget that what we're talking about is this. Just like in the diagram, you have 3, so you can have this and this. So that's what I have, E1, E2, and E3. So that's what I did. Take E1 intersect E2 is this particular one. Okay, E2 intersect E3 this particular one. Then E1 intersect E3 this particular one. And this particular one is this one. Okay, so this is the addition law for three events, but in the event that those three they are mutually exclusive. So that means you're going to have this, going to have this, going to have this. That is the mutually exclusive. Now, let us look at complementary events. All right, so complementary event. Now, if you recall from our set theory, called that E complement. If E complement is the complement, if EC, that's E complement, is the complement of the set, maybe, I mean, set E. Okay, then we're going to have E union of E complement is the same thing as the universal set. Okay, and also in the same set theory, we have the number of components in E union of uh, no, what I want to say is that when we have E, okay, intersect of E complement is actually null. All right, so now let's quickly look at that just as a form of recap. Let's say we have event E and we have the components as 1, 2, 3, 4, and 5. Okay, now E complements. Okay, let's have the sample space. Let's have a sample space of a number between 1 to 10. Okay, sample space between um, 1 to 10. Now, this is a set E. Okay, set E is 1, 2, 3, 4, 5. Okay, so then E complements will be things that are not in this, which are remaining in the sample space. So E complement will give us from 6, 7, 8, 9, and 10. That is E complement. All right, so then we have our E to be 1, 2, 3, 4, and 5. So let's say we have E union of E complements now. What will it be? Don't forget what I told you in the other video. So I'll just be straightforward with this. So we have 6, 7, 8, 9, 10 is not here, 1, 2, 3, 4. So that means our E complement, E union of E complement is going to give us 1 to 10. Okay. This is the same thing as the sample space. That's how we prove this. Now, let us now look at E intersect of E complement. Okay. Is there an intersect? This is does not. So it's naturally none. So it doesn't intersect. Okay, so that's just a way of explaining that further. Now, just take that one also out. Now, if we have, so we know that we have, of E union of EC. Okay, we have it as a sample space, as number of sample space. It's the same thing. So we can then divide, both sides by this sample space. We're going to have n number of union the complement divided by sample space. Then we're going to have this divided by sample space. So definitely this is one is going to give us the probability of E union of EC. Okay, that's probability, and this one is going to give us a 1. Okay, so probability of E union of EC is 1. Okay, but don't forget that we have this as the addition law. So if you put this one as addition law, union of EC, okay, it's going to give us a probability of E, okay, plus probability of EC, that's E complement, then minus probability of E intersect of EC. Okay, that's what it's going to give you. Now, because this particular one, don't forget when I did the other one, I told you that probability E intercept of A complement is null, is 0. So this particular one is going to give me 0. Then I'm going to have the probability of this plus this. Okay, then I already have this one as 1. So I'm just going to put 1 here. It's going to give me probability of E plus probability of E complement. So that is a complementary event. So we're going to look at one example now. All right, so in a single throw of 3 fair coins, find the probability of at least one head showing up. Now, we can say that let E1, okay, let E1 be event that at least one head, at least one head, you know, um, show up, okay, in the single throw of the 3 coins. So let's say E1 is the event that one head show up, and also let E2 be the probability that for no head, okay, no head, show up. Now, if you look at it this way, probability that one head show up and probability that no head show up, you will see that this is actually a complementary event. Probability that one head show up, probability that no head show up. Looks more of yes. If it's yes, and if it's not yet, it's going to be no. Okay, so that looks complementary. Now, how do we ensure that we find that one? Now, how do we do that? Now, this is something that I want you to be able to do. Okay, just do for uh 2 coins first. Okay, we have like an head and a tail here. For every coin we have head and tail, so you can do head here for 2 coins, head tail to know the event, tail head, and we have tail tail. So having done that, then I can bring all my events here. I have 1 2 3 4. Okay, I have 4 of them. I have head and I have head tail. I have tail head and I have tail tail. All right, so and I'm going to combine the event of just head and tail there. Okay, now what am I going to have here? I can have head here, can have head tail, and I can have head tail head. I can have head tail tail. I can also have tail head head. I can have tail head tail, then tail head, then tail tail. Now we are asked to find, so the sample space for all this is we have 1 2 3 4 5 6 7 8. Okay, so because of the 3 coin that is thrown, okay, the sample space is going to be 8. So we also have our sample space to be 8 because there are 3 coins, and the 3 coins have 2 sides. So 2 raised to 3 can also be 8. So the possible outcome that we have, there are 8 events happening, and the number of time of events E2 happening is 1. So this is it. That means no head show up at all in the single throw of the 3 coins. It's just 1 time. Then the probability, that is the number that at least one head show up, is 7 times. So our probability that okay, let's make just clean this place up. Okay, we already have that. Okay, let's clean that up for better clarity. All right, so like I said, the sample space, that's the number of outcomes, is 8. Okay, then we have the number of elements of events, E2. That means no edge showing up, is 8, and we have the number of elements in of no of at least one edge showing up is 7. Okay, now the probability of E1, okay, the event that at least one edge show up will be 7/8. Okay, so don't forget, what we're asked to find is the probability that at least one edge show up. Okay, so one edge show up is just 7/8. Okay, but we can move from, let's say, the probability of no edge showing up. Okay, the probability of no edge showing up, which is the E2, is probability of E2 is equal to 1/7. Okay, and don't forget, because we said that these are complementary events, the formula that we're given is that um, the formula that we give is that we have a probability of E complement plus probability of E. They are both equal to 1. All right, so if the probability of E2, and because if two events are complement, probability of E2 is 1/7, then the probability of E1, which is this one, will be 1 minus 1/7. And if you do that, you're going to have, okay, it's going to be um this is going to give us 7 oh sorry, 1/8 rather, because the sample space is 8. Okay, 1/8, that sample space is 8, that's the outcome is 8, so it's going to give us 1 minus 1/8, and if you do that, it's going to give us 8 minus 1, 7/8, which is the same thing as the one that we got directly here. Okay, just a matter of recap, we've been able to look at the complementary events, which we've just treated, and we also look at the addition law. We looked at combination of events. Okay, so if you say that the events are actually complementary, then you treat that way, as we have discussed. All right, I hope this video has been very, very informative for you. Want you to like this video, please subscribe to our YouTube channel, and feel free to share with your friends and loved ones. All right, so I'm going to see you next week, where we'll be looking at the another topic in probability. I'll be starting with independent and dependent events. So please don't miss that video. Independent and dependent events. We'll be looking at independent and dependent events, and also I'll be looking at conditional probability. We'll treat examples, and we'll also look at probability tree diagrams. We'll look at probability tree diagrams next week. So please don't miss that. Tell your friends to subscribe to these videos so that they can get more of it. All right. Thank you for watching. Bye.